In this video, we're going to take a look at plane curves and parametric equations. Um, and what we're thinking about here when we talk about plane curves are just curves that are in the plane. So in the xy plane, it can be any path. Usually we'll talk about the path having direction. So you'd have maybe some arrows drawn on the path. And what you can think about one way to think about this is oftentimes the parameter we'll talk about is t, and you can think about t representing time. It doesn't have to represent time, but it can be helpful for getting started on thinking about these parametric equations. And the idea is that if we follow along this path, maybe this is where we are at t equals 1, and maybe this is where we are at t equals 2, and maybe this is where we are at t equals 3. So for any given t value, we are at a very specific point, even though we happen to land at the same points more than once. If someone gives us t equals 5, we say this is exactly where we are. So we can think of the x and y coordinates as functions of t. So the points on that path would all be, x's and y's depending on a time t. You can see from the graph that y isn't a function of x because this doesn't pass the vertical line test, and x isn't a function of y because the graph doesn't pass the horizontal line test. But like we were saying, we can think of these x and y as functions of t. I should stick with the same letters as the book uses. So instead of x of t and y of t, we can say x would be some function f of t and y would be some function g of t. Right, so the x coordinate would be given and the y coordinate would be given, and those would depend on time. And then as time varies, the points that we land at will change, and we'll trace out this curve. Let's take a look at our first example. To get started, we'll start the same way we did when we were first learning how to graph things like y as a function of x. We made a table of values. Here we have t values and x values and y values. So we'll make a table of t values, and those will determine x and y. Let's use t equals, like, I don't know, -2, -1, 0, 1, and 2. Let's see what we get here. When t equals -2, x is -4 plus t, so it would be -6. And y is 5 minus 2 times t, so that in this case would be 9. When t goes up by 1, it looks like x should increase by 1 and y should decrease by 2. Let's see if that happened. Oh, -4 plus -1 is -5, so x did increase by 1, and 5 minus -2 is 7, and y did decrease by 2. And if we throw in t equals 0, we'll have -4 for the x and 5 for the y. And again, we can see x increased by 1 and y decreased by 2. Following that pattern, since t is just increasing by 1 every time here, we should have -3, -2 for the x's, and then 3 and 1 for the y's. So let's take a look at what this is going to look like. So what we've got here are pairs of points in these two columns together, right? So -6, 9, 2, 3, 4, 5, 6. Looks like this grid is 8 by 8, so this will be 1 off the grid. -6, 9, -5, 7, -4, 5, -3, 3, and -2, 1. And we can, it looks like this is going to be a straight line. We can include arrows on this line indicating the direction as t increases. So the arrows indicate the direction of increasing parameter. Okay, let's think about this a little more. One of the things we want to do is just take any line and be able to parameterize it. So here we were given the parameterizations, and we wanted then to just come up with a graph. But let's look at how some of the features of the graph connect with what we see in the formula. For example, let's focus on when t equals 0, we have this point 4, 5, or negative 4, 5. Notice that corresponds to the constants in the equations for x and y. So when t equals 0, negative 4, 5 was our point, and that ties into the constant here. What on x was negative 4, and the constant on y was 5. Alright, so another thing we want to think about, so negative 4, 5 we had was right here. That was when t equals 0. Let's also think about the slope of this line. We can see we go down 2 and right 1, so the slope is negative 2. So if we think about that as a change in y over the change in x, what we can write is a direction vector. We can put the change in x as the first coordinate of that vector and the change in y as the second coordinate. So when you list values like this is called a vector, and this is saying instead of going to a specific point, it's telling you how to move from a point. So this would be a positive 1 in the x direction and negative 2 in the y direction. And this would say move 2 in the negative y direction. To create the next point, right? And you can see that's exactly what we've done, right? We want to move 1 in the x direction and 2 in the negative y direction. And those are the coefficients on t. So notice that this is the coefficient on t in the x equation, and negative 2 is the coefficient on t in the y equation. So the coefficients on t in the parametric equations have to do with the slope, and the constant part has to do with the point that would be on the line when t equals 0. We'll look more at parameterizing lines at the end of this section. Let's look at some more just general examples first. Okay. Example 2 is asking us to sketch the curve represented by these parametric equations and write the corresponding rectangular equation by eliminating the parameter. Let's actually zoom back to that last example. We forgot that part. So it said write the corresponding rectangular equation by eliminating the parameter. We can see just from the graph that the equation of this should be y equals negative 2x minus 3, just from seeing that the y-intercept would be negative 3. Let's look at how we can get that if we weren't able to just look at the graph and easily determine it. So to do this, one possibility is solve one equation for t and substitute. So if I solve the first equation for t, I have t equals x plus 4. And then if I substitute that into the second, I have y equals 5 minus 2 times x plus 4. and that will become y equals 5 minus 2x minus 8, which is the same as y equals negative 2x minus 3, which is what we thought. So the main difference when we have a parametric equation is that induces or introduces some direction on the line. So if we just have y equals negative 2x minus 3, we have a line with slope negative 2 and with slope y-intercept negative 3, but there's not a direction. So when we have a parametric equation, set of equations like this, that tells us also like which way to put the arrows on the line, which direction it would be moving in. Okay, next one. So here we go. So let's take a look at this. If we want to sketch this, it's not going to be incredibly easy to pick points and make a table, but let's start that way, and it's not going to be what we want to do every time, but let's, again, just since we're kind of getting used to this, we'll start that way. So t, and then x, and then y. Let's do the same t values we did last time, so negative 2, negative 1, 0, 1, 2. X will be, it looks like 8 when t is negative 2. X will be 2 when t is negative 1, 0 when t is 0, 2 when t is 1, and 8 when t is 2. So we can see x does not depend on the sign of t, right? And the same for y, right? Whether t is negative or positive, the y is going to be the same. When t is negative 2, it looks like we'll have 17. When t is negative 1, we'll have 2. T is 0, we'll have 1. T is 1, we'll have 2. And t is 2, we'll have 17 again. So we see duplicated pairs, right? Some things to observe. X will only be positive or 0 because 2t squared will never be negative. And y is also going to be never any lower than 1, right? Because t to the fourth is going to be 0 or larger. So x is never lower than 0, y is never lower than 1. So this point 0, 1 is as far to the left and down as we're going to go. Let's make this 2, 4, 6, 8, and so on. So that we have a scale that we can work with. All right, so 8, 17 is going to actually be a little off our graph. It'll be up here. 8, 17, 2, 2 is going to be here. 1, 0, 1 is going to be here. Try to draw that more carefully. And now notice when t was going from negative 2 to negative 1 to 0, we were moving inward here. So when we get to t equals 0, we're at this point. But then we turn around and go back this way. As t increases for positive values, we head back out away from the origin, or away from that point 0, 1. So it's a more interesting path. It's not one direction. It comes in and then goes back out. Right? Then it's also asking us to write the corresponding rectangular equation by eliminating the parameter. This looks like a parabola, so that gives us a clue about what we're expecting for the rectangular equation. Notice here that solving either one of these for t is going to involve having a positive or negative square root. So we don't want to do that if we don't have to. We can notice here that t to the fourth could be thought of as t squared squared. So instead of solving for t in the x maybe solve for t squared. If we solve for t squared, which we could replace in y, we'd have x over 2. Right? And then y would be t squared squared, so x over 2 squared plus 1. So y would be x to the 4th over 4 plus 1. So not a parabola, but at least a degree 4 polynomial, right? Shifted up 1 like we're expecting, but that particular graph would also have a branch on the left side of the y-axis, and this does not have that. So what we have to include is a restriction that x is only greater than or equal to 0. So when we write down the rectangular equation, we want to make sure that we get an equation that represents exactly what this graph would be. So that restriction is critical. Otherwise, y equals x to the 4th over 4 plus 1 would have y-axis symmetry. There would be a piece on the other side as well. This is probably a good time to grab your graphing calculator and talk about how to graph parametric curves on your graphing calculator. We want to get started just like we did with polar. So go to mode and change from function to PAR for parametric. And then once you've done that, when you hit your y equals button, now we can see we've got pairs, x1 of t, y1 of t, and then the next pair would be x2 of t, y2 of t. So we always have to enter an equation for x in terms of t and an equation for y in terms of t. So I'll do that too, and then again my input, if I hit this x button, is going to show up as t when we're in parametric mode. So 2t squared I want for x, and t to the 4th plus 1 for y. Not plus 11, just plus 1. And then in your window, you can notice we've got a t min, a t max, and a t step. Just like in polar we had theta min, theta max, and theta step. And then we also have the standard, what window do we want to see for the x's and y's. So here we wanted to take some negative t values, so let's try negative 3 to 3. The t-step, if you keep it relatively small, the graph will look smoother, just like the theta step being small helps those graphs look smoother. If you have it large, it'll look like a kind of a choppy polygon graph. Okay, so let's leave the x's and y, well, let's do it maybe negative 5 to 5 for the x's instead. And these y's were not expecting to be negative, so I'm going to do negative 1 to 20 maybe. Maybe 25. So it's like what we were expecting, right? So for a large value, when x is 5, we would have 5 to the 4th for y, so that would be really tall. If we go to window and do, or zoom and do a zoom fit, that will change the y's to be in the range we want. The key is that mode to be parametric, and then on your window to keep a small t-step again. So if we do t-step, it's like 5, just so you can compare. The graph is choppy and it doesn't go as far as we want it to go. So that's kind of a key thing, is keeping that t-step relatively small. All right. Then the next one, sketch the curve represented by this set of parametric equations and then write the corresponding rectangular equation. Let's see. Maybe we'll make another table of values. So t, x, and y. And before we do that, let's think about things that we notice about restrictions for x or y. So x is the absolute value of some expression. That expression is never going to be, that value for x will never be negative. It could be 0 when t equals 1, but if t is not 1, x is going to be positive, right? Because it's the absolute value of an expression. Y, on the other hand, can range from any negative value to any positive value. So y can be anything, right? Let's also think about what happens as t increases. Y will increase. And let's see. That's good enough. For a while, x is going to decrease and then x is going to increase. So we'll look at that from the graph. But at least we can see as t increases, y is going to increase. So let's look at some, again, charting some values. If we do -2, -1, 0, 1, 2. Let's add another 1 on there, 3. We know that when t equals 1, that's going to be a point where things change for x. So we want to make sure we have a few points on either side of that t equals 1. Okay, so when t is -2, we'll have -3 in absolute value for x, so that'll be 3, and we'll have 0 for y. When t is -1, we'll have absolute value of -2, so 2 for x and 1 for y. When t is 0, we'll have absolute value of -1 for x and 2 for y. T equals 1, we'll have 0 for x and 3 for y. And y is just going to keep going up by 1. But now the x is going to change. When t is 2, we have 1. When t is 3, we have 2. So we see this pattern in x's. They were decreasing for a while, and now they're going to increase again. So we've got 3, 0. When t equals -2, 2, 1. When t equals -1, 1, 2. When t equals 0 and 0, 3. When t equals 1, then 1, 4. So same x but a different y. 2, 5, again, same x as this other point but a different y. So what we see is it looks like an absolute value graph on its side. And if we draw directional arrows on here, as t increases, y is increasing, so we're following this graph upward. Okay, so if we want the corresponding rectangular equation, you want to maybe solve one of these for t. It looks a lot easier to solve the y equation for t. So I'd have t is y minus 2, and then sub that into the x equation. So we'd have x equals the absolute value of y minus 2 minus 1. And this is our expression for t. So what we have is x equals the absolute value of y minus 3. This makes sense, right? It's an absolute value graph turned on its side. So instead of a y equals, we have an x equals. And it seems to be shifted up 3, which fits with the y replaced with y minus 3. And we don't have any restrictions on this graph because y gets to be anything, so we would get the entire absolute value graph. And let's look at that on your calculator too. So if we get rid of our last set and we do absolute value, that's under math and then number. So absolute value of t minus 1 for the x coordinate and t plus 2 for the y. Here we'll just do x from, let's do -2 to 6, and the y from -5 to 5. So, looks like we expected. Alright, now something that's going to involve some of the trig we've done earlier and some of the conic sections as well. This is asking us to sketch the curve represented by these parametric equations. X equals 2 cos theta, y equals 6 sine theta. And once we have our sketch, write the corresponding rectangular equation. Let's just think about what x and y ranges would be. So x is 2 cos theta. That's going to be stuck between -2 and 2, right? There's no way it's going to be larger than that because 2 is the amplitude of the cosine function. And similarly, y is going to be trapped between -6 and 6. Right? Because the amplitude for 6 sine theta is 6. So we'll get as high and low as 6 and -6. And then let's just look at a few specific theta values. If theta equals 0, we'll have 2 cos 0, which would be 2, and 6 sine 0, which is 0. When theta is pi over 2, we'll have 2 cosine pi over 2 and 6 sine pi over 2. When theta is pi, we would have -2 and 0. And when theta is 3 pi over 2, we would have 0 and -6. Alright, so theta equals 0 was 2, 0. Theta equals pi over 2, we have 0, 6. Theta equals pi, we have 0, -2. Theta equals 3 pi over 2, 0, -6. This is almost exactly the same way we defined the trig functions. Without the 2 and the 6, we would get a unit circle, and we defined the trig functions to be the x coordinate on the unit circle is cosine theta, and the y coordinate on the unit circle is sine theta. So instead of having a circle, we're getting an ellipse because the x coordinate is stretched by a factor of 2 and the y is stretched by a factor of 6. So these are parametric equations for an ellipse. The way this is set up, we are going to be traveling counterclockwise around. Because this was t equals 0, this is t equals pi over 2, this is t equals pi, and this is, oops, not t, theta. Doesn't matter what name you use for your parameter, but since they use theta, I better use theta too. Right? So we're traveling around this ellipse in the counterclockwise direction. To get rid of this parameter, we're going to do something different. We're not going to solve for theta and substitute because that's going to be pretty messy. What we're going to do is rely on this Pythagorean identity that we know cos squared theta plus sine squared theta is 1. Cos theta is, in this case, x over 2, and sine theta would be y over 6. Right? So what I'm going to have here is x over 2 squared for cosine squared, and y over 6 squared for sine squared, and that's going to give me 1. So we've got x squared over 4 plus y squared over 36 equals 1, and that's what we were expecting for an equation of an ellipse if it has a minor axis on the x-axis, length 4 or width 2 halfway across, and then our major axis is on the y-axis, and the length for the major axis is 12 or twice 6. Alright, and the next one is asking us to start by looking at our graph from a graphing calculator. So let's take a look at that. X equals secant theta, y equals tan theta. This one's a little more interesting than some of the others have been. So secant, we want 1 divided by cos theta, or cos t. Even if the equation lists it as theta, you can call it t on your calculator, that's no problem. And then tangent of t, theta. The period for secant is 2 pi, right? So let's do 0 to 2 pi so that we cover all of the x values. Oops. The period for tangent is just pi. So to cover all the y values, we would only need pi, but to cover all of the x's, we need 2 pi. And secant and tangent both have range from like very large negative numbers and very large positive numbers. Secant misses some in the middle, right? But let's do like negative 20 to 20 for both x and y just to get a good picture. This looks a little bit like a hyperbola, and it should. That's what it is. So that gives us a clue about what the equation might look like when we get rid of the parameters and get to a rectangular equation. And let's do that. So similar to the last one, in the last one we used cosine squared plus sine squared is 0. Here we want one of the other, or sorry, is 1. Here we want one of the other Pythagorean identities involving tangent and secant. So remember, if we divide all of this by cosine squared, we have 1 plus tangent squared is secant of theta squared. So in this case, that's going to look like 1 plus y squared equals x squared. And if we rearrange that, we've got x squared minus y squared equals 1. So we have that hyperbola that we were expecting. We've got a difference of squares on our variables. So if we say, this is 1, 2, 3, negative 1, negative 2, negative 3, 1, 2, 3. Let's sketch this. So it's going to open in the x direction. We have this point 1, 0, and that point negative 1, 0. We can sketch our central box here. And put in our asymptotes, connecting the corners of that central box. And then we can get a graph of this thing. I don't want to put arrows on yet. I keep doing arrows. No arrows yet. That's the interesting part here. Okay, so let's make a graph of secant theta and a graph of tangent theta. Maybe on the same set of axes. So let's do theta, this is pi over 2, pi, 3 pi over 2, and 2 pi. All right. Secant of theta I'm going to do in blue. Secant of 0 is 1, and then we are positive until we get to here, and then we have an asymptote. And then we're negative on this stretch. And then positive again on that stretch. Then let's see, tangent of theta I'll do in red. Has the same asymptotes as this because it's sine over cosine, so the same problem points for tangent and secant. And when we're between pi over 2 and pi, tangent is going to be negative. And then when we pass pi, between pi and 3 over 2, tangent is positive again. All right, so what we've got here between quadrant 1, x and y, which are secant and tangent, are both positive. Let's not write quadrant 1, let's write this way. So for theta between 0 and pi over 2, x and y from this parameterization are both positive, right? And they're both getting larger. So that means this branch is going to be for theta between 0 and pi over 2. And as we get closer to pi over 2, we get further and further from the origin. Then for theta between pi over 2 and pi, the x and y, the tangent and the secant are, or secant and tangent are both negative. And that happens over here. And the closer we get to pi, the closer the tangent value gets to 0, and the closer the secant value gets to 1. So we're moving in toward that point, and this is for theta between pi over 2 and pi. Then, for theta between pi and 3 pi over 2, the x-coordinate is negative, that's the blue line, and then the y-coordinate, which is the red line, is positive. So the x-coordinate, our blue line, is negative, the y-coordinate is positive, which means we're in this quadrant here. So that's for theta between pi and 3 pi over 2. And then the last branch for theta between 3 pi over 2 and 2 pi. We can see the x, which is tracked by this blue line, that's positive, and the y is negative. Right, so that means we're down over here. The points on the graph are in quadrant 4, and we're getting closer to the point 1, 0 as we get closer to 2 pi for theta, so we're moving in that direction. So it's a hyperbola, but it's traced out in kind of a strange way. We go along this way, and then back across over here and up, and then back here to get back to the starting point. In example 6 here, we've just got another pair of parametric equations, and we're trying to come up with what the graph would look like, and also just to get rid of the parameter and get the corresponding rectangular equation. So it says to use a graphing calculator, but let's think through this first a little bit before we grab our calculators and think about at least what are the restrictions on x and y involved here. So x is going to be the natural log of 2t. So this is a little bit strange. We're not used to having x be our vertical axis, but this is just another way to think about this. So if t is our input and we want to track what the x values are doing, t cannot be negative for the natural log function, right? So when t is, let's see, a half, we'd have natural log of 1, which would be 0. And the closer we get to 0 for t, the further in the negative direction these x's are going to drop. And then they would grow slowly as t increases. So x will increase as t increases. T has to be greater than 0 because of the natural log function on x. And then y, we would also graph only for values of t that are greater than 0. So it wouldn't include 0, but y is t squared. So y is going to grow more quickly than x, right? Both are going to be growing when x is large and negative. Y is going to be getting closer and closer to 0, right? And then y is going to grow as x grows. So you can kind of think about what's going on with each coordinate individually. And I would would say also, before we grab our calculator, let's maybe try to eliminate the parameter. If I solve for t in y's equation, I would have t equals positive or negative square root of y. Well, I don't want to mess with the positive or negative square root part, so let's not think about that. But if I solve this expression for t, I would have e to the x equals 2t. So t is e to the x over 2. Alright, and then if I substitute that into the expression for y, I have y equals e to the x over 2 squared, which is the same as e to the 2x over 4. So we're expecting an exponential graph and cut by a factor of 4. So we're expecting roughly a graph that has this shape. So let's see if we get that on our calculator. So remember to switch your calculator to parametric mode if it's not already there. Mine is already there. Then when you go to y equals, you'll have these sets of equations come up. We can enter them in pairs. So we want natural log of t for x. And, natural log of 2t. And we want t squared for y. And for our window, we only want positive values of t, so we'll leave it at 0 to 20. And the x's are going to be some negative, so let's do, I don't know, negative 10 to 10 for the x's. And if this is really an exponential graph, let's make our x scale 1, the y's won't be negative, so I'll leave that at 0, but they're going to grow very quickly, so I'll make this, I don't know, 1,000. Let's graph it and see what it looks like. So we can see that it has the right shape. If I want to see more of the graph, I would need to increase my t max. So if I make my t max, I don't know, 100 instead of, or 111 instead of 20, go back to the graph. Now it'll extend a little further, at least. If I want to see this part to the left of the x-axis, I would want to decrease my y max so that I'm seeing closer to the x-axis. So make my y-axis, or y max maybe like 4, so I'm just seeing 0 to 4. And again, it's dropping down so quickly that we can still hardly see it. Let's change that window again, make it 0 to 0.1 for the y max. Now we can sort of see something here. It looks like the graph just stops there. The problem is that it just is indistinguishable, I think, from the y-axis, so the calculator is not connecting those points. Let's see. That's probably good enough for that example. All right, then the next thing we want to look at is these sets of parametric equations for projectile motion. And these equations will be used extensively in physics, and you'll see them again in Calc 2 when you get there. So we're not going to prove these equations, but we'll just use them and solve applications using them. So what we've got here is, if we know the angle at which a projectile is launched, and we know its initial speed, and we know its initial height, then we can use these equations, but we really have to be careful with the units. So if your velocity is given in feet per second, then t would have to be in seconds, h would have to be in feet, and then we would use the gravity constant, 32 feet per second per second. That's the acceleration due to gravity, and the units, feet in seconds at least. If the velocity instead is given in meters per second, then you would want to use t in seconds still, but the height would need to be in meters, and you'd use the gravity constant 9.8 meters per second instead of 32. So usually to use these, you want your velocity to be in one of those units, either feet per second or meters per second. If it's not in one of those units, then you would probably want to switch it to one of those and then use the rest as explained here. So let's take a look at example 7. A ball is thrown at an angle of 45 degrees, so that's our theta, to the horizontal with an initial speed, which is our initial velocity, 40 feet per second. So that's one of those that we can use right away. And from a height of 5 feet, so that's our h. So we've got everything we need to fill in and just set up the equations, so x and y in terms of t. So it's saying x is going to be v naught, which was 40. Cosine theta would be square root of 2 over 2 times t. And y would be negative 1/2 times 32 in this case, so negative 16 t squared plus v naught, which was 40, sine theta, which is also square root of 2 over 2, times t plus the height, which is 5. So let's clean these up a bit. So we'd have 20 times the square root of 2 times t for x, and negative 16 t squared plus 20 square root of 2 t plus 5 for y. So those are our parametric equations for this path. Then if we want to know how long is the ball in the air, we would want to be figuring out when the height is 0. So when does y equal 0? So we don't need a connection between x and y to answer this question. We just really need a connection between y and t, right? So we'd set y equal to 0. And probably use the quadratic formula for that. So we'd have t equals negative b, or the opposite of b, plus or minus the square root of b squared, which would be 400 times 2, so 800, minus 4ac, which is going to be plus 20 times 16, so 320, all divided by negative 32. And then grab a calculator and get that value approximately. So negative, this and all in parentheses, negative 20 times the square root of 2. Let's try the minus first. Negative square root of 800 plus 320 would be 1120. Divided by negative 32. So like 1.93 seconds to the nearest hundredth. If we wanted to check the other one, you can change this minus to a plus. And that's a negative value, so that doesn't make sense. But it does make sense that for a negative t value, we would have the other place where y would be 0. So if we went back in time and the ball were going down lower than 5 feet, that would be sensible for the other value of t that would make y 0. So it looks like 1.93 is roughly what we want. So about 1.93 seconds for the ball to be in the air. When is the ball at its maximum height, and what is the maximum height? Probably the easiest way to answer this is to relate x and y to each other, and then figure out what kind of graph we're looking at. So let's see, if we get rid of the x, we would have t is equal to x divided by 20 square root of 2. And so we've got then y is equal to negative 16 x over 20 square root of 2 squared plus 20 square root of 2 times x over 20 square root of 2 plus 5. So y is equal to, let's see, negative 16x squared over 800 plus x plus 5. 16 over 800 we can reduce. Oh, 16 over 800. 0.02, so 200ths, so 1/50th. All right. So what we're looking at is a parabola opening downward, which we knew. And so the maximum height is going to be the vertex of the parabola. In this case, x is negative b over 2a, which is negative 1 over negative 1/50th. Oops, negative 2/50ths, which would be 25. And y would be negative 1/50th times 25 squared plus 25 plus 5. So 17.5. So the max height is going to be 17.5 feet. And the x coordinate is 25, but the question was when. So we want to know what's t. So if x is 25, t would be 25 over 20 square root of 2. So let's get that approximately. So we get like 0.88 seconds roughly. So at the time about 0.88 seconds, we've got the maximum height of 17.5 feet. And the last thing it's asking us to do is to use our calculator to graph those equations. We know it's going to be a parabola opening downward, and we know where its vertex is going to be, and we know it's going to start at height 5, so we should be able to know what to expect from this graph. Let's take a look and make sure we get that. So I'll get rid of these equations. So for x we had, what, 20 times the square root of 2 times t? There we go. And for y, that was negative 16 t squared plus 20 times the square root of 2t plus 5. the window, that makes sense. We can leave the t's as they are. Actually, when t is 0.88 seconds, that's when the ball is going to be at its max height, and it was going to hit the ground at 1.93. So let's just do actually 0 to 2 so we can see the path up and then back down to the ground. The x's aren't going to be negative. We're going to start with 0. And the vertex was at 25, so probably if we go out to 50, that should give it time to go up and back down. And then, let's see, we can change the scale to 5 or 10. Y-min, we're not going to have negatives. Those would be after it landed on the ground. And the Y-max we had, the vertex was 17.5, so let's do 20. And take a look. Let's see that window again. So the t-min 0. When t is 0, we should see that part where it's arching up. Let's take a look again. Did I enter it incorrectly? 20 times the square root of 2 times t. Oh, I missed a t on my y input, so hopefully yours looks better. So I want 22 times the square root of 20 times the square root of 2 times t plus 5. Now hopefully it'll look right. That looks better. And there's the parabola we were expecting. Except that we were expecting that it would hit the ground. Let's change our window a little bit to, I don't know, 60 for the x-max. There we go. So we have to go a little bit wider to be able to see it hit the ground. All right. Then we want to look at parameterizing lines. We looked at an example of a parameterization of a line at the start of this section, but what I want to do here is just talk more generally about how you could parameterize a given line. So let's picture, we'll work with the form we're used to. So if we have a like y equals mx plus b. So if we know the slope of the line would be m, which we could think of as m over 1. And we can think of that as the change in change in y over the change in x. And if we have a point on the line that we know, in this case we would know 0b, that would be the y-intercept. Then what we could do is take a parameterization of the line to be x is the x-coordinate of the of the y-intercept plus the coefficient on the change in x, which in this case would just be 1, times t, and y would be the y-coordinate of the y-intercept plus the m, that coordinate or that coefficient on t. So what we can see here is each time t increases by 1, y will increase by m and x will increase by 1. So the ratio of change in y to change in x is m over 1. And also, when t equals 0, we get the point 0b, which we know is supposed to be a point on there. So this is one possibility. But let's think about specifically maybe like y equals 2/3 x plus 1. So we know that goes through 0, 1, and we know that the change in y over the change in x is 2 to 3. So we'd have this as 1 point, up 2 over 3. There's another point. Alright, so if this is our line, I'm not going to put arrows on it yet because the arrows would be determined by the parameterization, but if we have that line and we somehow want to trace it out, so using the option that we had given, we would have x equals 0 plus 3x, or actually, sorry, just 1 times t, not 1 times x, and then y would be 1 plus 2/3 t. So just doing 1 for the coefficient on t and x, and then the slope, which is 2/3, is the coefficient on t and y. But what we really need here is not these specific values necessarily, but just the ratio to be 2/3. So another option would be x equals 0 plus 3t and y equals 1 plus 2t. Because then when t increases by 1, y will go up by 2 and x will go up by 3. So the ratio of change in y to change in x would still be 2/3. And that's what we want, right? Or if we're thinking slope is 2/3, we could think, well, 2/3 is the same thing as, for example, let's do negative 10 over 15. Negative 15, right? So that's the same ratio. So as long as the ratio of the coefficient on t in y to x is 2 to 3, everything's fine. So another option would be 0 minus 15t for the x, and y equals 1 minus 10t for the y. Right? So we could go on and on and on and on here. If we make these both negative, then the direction of the line is going to be downward and to the left. But if we have coefficients on x and y, on t and x and y positive, then the line is going to move upward and to the right. So just depends on the sign of those coefficients will determine the direction of the line. Other options would be, instead of using this point 0,1 that we have on this line, we could use this point 3,3, or we could use this point 6,5. Let's use that one. So I could say instead of 0,1, 0,1, 0,1 for the start of these, let's use 6,5. So I could use x equals 6 minus 15t, y equals 5 minus 10t. It's going to trace out the same line. Right? It's going to go through when t equals 0. We'll have the point 6,5. And the slope will be the coefficient on t and y to the coefficient on t and x. So same line as we had, just a different way of defining it. So in general, what you want is x equals, let's say, x naught plus, let's write at, and y equals y naught plus bt, where the restrictions we have here are x naught, y naught is any point on the line, and the slope of the line would be the change in y over the change in x, which is the coefficient b to the coefficient a. So that's the general pattern for what you want to do for parameterization of a line. Then we want to turn our attention to parameterizing circles in a more general way than we have already. We want to be able to say if we know the center of the circle, is, let's say, hk, and if the radius is r, how can we find a parameterization of that circle? So given the center and the radius would define a unique circle, and then we want to come up with parameterization for it. So our standard circle, our unit circle, we know a parameterization for that is just x equals cos t and y equals sine t. Right? If I want to adjust the radius, say I want radius 2 or 3 or 5, then what I want to do is expand the circle. So I want to basically stretch it vertically and horizontally by the same factor. So what I would want to do is make it x equals whatever my radius is, cos t. That will allow x to range from negative r to r, and then y to be r sine t. That will allow y to range the same, negative r to r. So that would just stretch the circle and make it wider. Also, for an ellipse, you would just stretch x and y different amounts. So we'll talk specifically about circles, but you could do the same thing for the ellipse. If x should be doubled and y should only be left the same, that would make a wider ellipse than it is tall, and you can adjust that coefficient to get an ellipse the way you want it to be. So that's how we would adjust the radius. And if we want to adjust the center, normally we would replace x with x minus h and y with y minus k. So we would have x minus h equals r cos t and y minus k equals r sine t. But we don't want the minus h and the minus k where they are. Instead, we want just x equals r cos t plus h, whatever the x coordinate is, and y equals r sine t plus k, whatever the y coordinate is. So those would be the parameterizations, the standard ones at least, for a circle of radius r, center hk. So for example, if I want the circle with center 3, negative 2, let's say 3, negative 4, and radius 2, I could say x equals 3 plus 2 cos t, and y equals negative 4 plus 2 sine t. So the radius 2 shows up as the coefficients on cosine and sine, and the center shows up 3, negative 4 as the constant term in each of those. Another thing we could do would be that's going to trace the circle counterclockwise, the same way our standard parameterization is set up when we defined the trig functions. If we want to change the direction, there are many options, but the easiest is to make t opposite. I'm going to pull up a calculator here and we can kind of see this in action. So switch to parameterization or parametric mode. Looks like I'm already there. Go to y equals, get rid of these. So if I have 3 plus 2 cos t and negative 4 plus 2 sine t, I leave them like that. Let's change our window here. I want to do 0 to 2 pi for t's. So we can leave t step at 0.1 for now. X-min, let's do 0 to 7 maybe. Let's see. Yeah, that should be fine. And y's, X scale we'll leave as 1. Y's we want to have lower. I'll do negative 7 to 1, something like that. Let's take a look. So, wait a second. Negative 7 to 1. This is still not going to look exactly circular, but we can see it is hitting the right points. Then we can also see that that traced counterclockwise. If I change my y equals so that there's a negative t here instead of a t, cosine of negative t is the same as cosine of t, so that wouldn't do anything different. But if I do sine of negative t, that's going to make that opposite. So the x is going to still be moving the same direction as it was before, but the y will go opposite. So we're going to start off going downward and left instead of upward and left. Let's see how this will work. See, it went down and around instead. Yeah, so that would change the direction. Another way to change the direction would be if I make this 3 plus 2 sine t. So put sine where cosine is, and then negative 4 plus 2 cosine t. That's going to change the direction. It's also going to have a different starting point. When t is 0, we would be at 3 for the x, and then looks like negative 2 for y. So we'd be at the top of that circle, and it's going to start at a different place and also go probably clockwise instead of counter. Let's take a look. All right, so it's going to start at a different place and also go clockwise instead of counterclockwise. So one way to change the direction is to change the sign on t. Another option, which would also not just change the direction but change the starting point, we could do x equals 3 plus 2 sine t, and y equals negative 4 plus 2 cos t. So the parameterization here that I have in the box is going to be center hk and radius r, and it's going to trace counterclockwise. We can adjust the radius by changing r, adjust the center by changing h and k, and then adjust the rotation direction by making either t opposite or switching the sine and cosine around. And lastly here I have some matching problems. I can't seem to quite fit it on the same screen. Let me see if I can zoom in out a little bit here. Okay. So hopefully you can see all of the graphs as well as at least some of the formulas. I'll zoom out one more time. Okay. So what we want to do here is try to put together, like match up the graph with the right formula. And it helps to think about different restrictions on x and y, as well as relationships between x and y together. Let's see, I'm trying to think of what are they going to be the easiest ones to start with. So let's look at b. Both a and b don't involve anything with sine and cosine. So that's one thing to notice, at least, right? But if we look at b, we've got x equals t squared minus 1 and y equals 1 minus t squared. The thing that's easy to observe, or at least relatively easy to observe on this one, is that x and y are opposites. Right? One of them is t squared minus 1, one of them is 1 minus t squared. So they're opposites. Also notice that x, since it's t squared minus 1, is not going to be any smaller than negative 1. T squared is always 0 or positive. So x is going to be bigger than or equal to negative 1. And let's see about y here. 1 minus t squared, y won't ever be any larger than 1, right? So x is always bigger than or equal to negative 1, and y is always either going to be smaller than or equal to, oops, I wrote that the wrong way, slide it the right way, smaller than or equal to 1, because I'm subtracting t squared from 1 to get y, right? So noticing those restrictions, x can be anything bigger than negative 1, and y can be anything less than or equal to 1, and noticing that x is equal to the opposite of y makes it clear that graph 3 is the right one here. So we figured out this is B, this is 3. All right. Then let's take a look at maybe the first one. So A, where x equals t minus t cubed and y equals t squared plus t. One thing you can notice is when t equals 0, we didn't pick any specific points for the last one, but this one we could notice when t equals 0, we would have actually the point 0, 0 on the graph. Right? So the only two graphs that we have left here, ruling since we're done with 3, that have 0, 0 on the graph are the first one and the fifth one. I guess it's labeled. So number 5 and number 1. The fifth one has a lot of rotation that looks a lot like trig functions. So if I were to just guess, it seems like graph 1 is probably the one here. Let's think a little more carefully also about what's going on as t gets larger and is in a positive or a negative direction. So I'm trying to think about lots of different ways to think about these problems. So one, like we saw in the first one, is to notice relations directly between x and y, and also to look at restrictions on x and y. Here we've started looking at, well, you can always grab specific t values and see some points that are on the graph. And then another good thing to look at is general trends. So as t gets really large in the positive direction, what happens to x? What happens to y? And remember, the highest degree term is going to dominate what's going on. So this negative t cubed would dominate the x, and the positive t squared would dominate the y. So we would say x would be going to negative infinity, but y would be getting larger in the positive direction. So the graph would be moving left and upward. In an unbounded way. And as t goes to negative infinity, or as t gets unbounded in the negative direction, x would be large unbounded because the opposite of t cubed would be large negative, or sorry, large positive, and y would still be unbounded in the positive direction. So we would have right and upward motion. So both of those things are fitting with graph 1 if we can imagine this graph continuing that way and this way. That seems to fit with what we're seeing, left upward and right upward movement. So A, seems to be graph 1. B is graph 3. So 2 down. I'm going to erase all this so that I have some space. So looking at specific points, looking at general trends as t gets large or t gets small. Some of those same techniques are going to work with D here. So let's take a look at D, which is x equals t plus cos 2t and y equals t plus cos t. Let's do that specific, like if we take t to be 0 again, we would get the point 0 plus 1. So 1, and then 0 plus 1 for y also. So 1, 1 is a point on the graph. And then also, let's think about as t goes to infinity, x is going to also just be growing larger, larger, larger. This cosine 2t is going to oscillate between -1 and 1, but t itself is just going to get huge. So x will go to infinity, and y will go to infinity also. So we'd see upward and right movement. And it will be unbounded. And as t goes to negative infinity, so as t gets unbounded in the negative direction, x will get unbounded in the negative direction, and so will y. Again, these cosine terms will keep the movement from being linear, but it won't impact it too much. So we'll have left downward motion. So all of that seems to fit with probably graph 6 here. We see that's the only other graph left that's going to be unbounded. The others seem to be trapped within certain values. So graph 6 must be D. Oops. Lowercase d, I guess. So 3 done. Then, let's see, probably graph C might be the next easiest to determine. X equals sine 2t and y equals sine 5t. So notice that C and E and F are the only ones that are left, right? But let's see, let's see, all of them have cosine and sine of some other things. Cosine and sine or sine. The outside functions are either cosine or sine, which means for all of them, x and y are going to be trapped between -1 and 1. So just that much information isn't going to help us here. Thinking about other techniques we've looked at, we can see this graph goes through 0, 0, and the others don't. So we could say when t equals 0, it doesn't have to be just when t equals 0, but that's what it happens to be here. T equals 0 would give us the point 0, 0, which means that the only graph that's left that goes through 0, 0 is the graph 5. So this must be C. But also notice that we've got this ratio of cycles that would go twice as fast as normal to cycles that would go 5 times as fast as normal. And you can kind of see that here, that the cycles for y are happening faster than the cycles for x back and forth. So that part also seems to fit with the sine 2t, sine 5t. So then we've just got 2 of these left. X equals cosine t minus cosine t, and y equals sine of t minus sine t, and x equals sine t, y equals cosine of t plus cos 2t. So let me erase this, and So the remaining pairs of equations we have are E and F, and the remaining graphs are 2 and 4. Notice that for these sets of equations, E and F, the only one that's very familiar to us would be x equals sine t. The others are kind of unusual because they have a cosine function within a cosine function. So cosine of t minus cosine t, or sine of t minus sine t, neither of those would be necessarily that familiar to us. But we can at least notice that because we've got cosine and sine on the outside, we're still going to see that x is between 0, negative 1 and 1, and y is between negative 1 and 1. But the same is true for the parametric equations here in F. This x-coordinate has to be between negative 1 and 1, and this y has to be between negative 1 and 1. So that's not going to help us distinguish one graph from the other. Probably one thing to do would just be to pick a t-value and see what the point looks like. So if t equals 0 on this first graph, x is going to be cosine of 0 minus cosine of 0, which is cosine of negative 1, 0 minus 1, which is cosine of 1, and you can use your calculator and figure out that's about 0.54. And y is going to be sine of 0 minus sine 0. Sine of 0 is 0, so this is just sine of 0, which is 0. So we have this point on here, 0.540. So between these two graphs, we only see one of them that has a point in the vicinity of 0.540, and that looks like this one. So this must be graph 1. And, oh, sorry, not 1, 2. 4. Can't read where my numbers are. And 4 would go with E. Those sets of equations. And then for the other one, let's make sure it looks feasible. So at least with this one point, when t is 0, again, we'd have x equals sine of 0, which is 0, and y equals cosine of 0 plus cosine of 2 times 0, which is still 0. So we've got cosine of 0 plus 1, cosine of 1, which is about 0.54. So we should see a point 0 for x, 0.54 for y. It looks like we see that up here. So graph 2 seems to be with this set of equations in F. F is graph 2. So hopefully these matching problems can help you be a little more familiar with how parametric equations and the graphs fit together.